Okay, this is a continuation in a series of videos whose express purpose is to show you how to solve various kinematic problems effectively and quickly using the SUVAT method. Now, I'm assuming that you've seen the introductory video that I have. In case you haven't, I will put the link to this video in the show more at the bottom of the screen that you're looking at. If you just expand that out, the link will be there. Hopefully all these videos are part of a playlist and it's at the top of the playlist. But anyway, I would encourage you to look at this video, and here is just a brief scroll down of what's on it, and you can pause the video if you want to read that better. Alright, so let's get back here, and just want to remind you that when you're looking for kinematic problems, you're looking for problems that have either constant acceleration or constant deceleration, and they contain some of the SUVAT information: displacement, velocity, initial or final or both, and time. And you're not concerned with forces or mass or energy, so no newtons, no kilograms, no joules. Those are dynamic problems when you're dealing with forces, and static problems, and then with energy, total and potential energy, that's another subdiscipline of mechanics. Just want to remind you that the SUVAT method is a simple systematic approach that's 4 steps. 1, you write SUVAT vertically. 2, you enter 3 out of the 5 SUVAT variables next to their letter. Circle the variable you need is step 3. And step 4 is draw an arrow through the variable that's left and use the equation that's affiliated with that variable to solve for the circled variable, or unknown. So you'll have something that'll look something like that, not exactly, but you're going to have at least 3 out of the 5 bits of data and an equation that is going to be easily found through this method. So you'll be seeing this throughout this video, as I've shown in the other videos with each of the problems we'll do. And if you haven't memorized this yet, as long as you keep looking at it, it'll sink in. There are certain patterns that I'll mention how to memorize it quickly in the introductory video. Some tips on memorizing quickly there, if you want to look at that. So the SUVAT method is essentially like a simple algorithm that will lead us to the equation very quickly, and on a time test that's very nice. Okay, so let's look at the first problem here in this video. Now, if you looked at the previous videos, in fact the one that preceded this one, I had this problem there, but I'm asking a different question now. So let's read it, and it says it's a rocket is launched at 20 meters per second vertically upward from a platform extending from the roof of a building, and then as the rocket returns downward, the platform is removed and the rocket hits the ground 6 seconds later after it was launched. So what is the rocket's final velocity right before it hits the ground? Okay, before we ask how high was the rocket when it launched. In other words, how tall was the building? So we have exactly the same information, but we're asking a different question this time. And just to remind you that this is a free fall type problem. It's a one-dimensional motion problem with there's no air resistance. I didn't mention that, but there's no air resistance, and so it's falls under the definition of a free fall problem. The reason we pulled the platform out is so it could go straight up and straight down, which makes it one-dimensional motion. Okay, so let's look at our information that we've got here. Step 1, well, even before step 1, we want to make sure that we've got constant acceleration, and we do. It would just be the g acceleration minus 10 meters per second squared, and that's makes it a free fall problem. Okay, the other thing we have is that the initial velocity u was 20 meters per second, and that it fell, t was 6 seconds, and so we have 1, 2, 3 bits of information, so we can put that in there. We've got 20 meters per second. Up is positive. We're going to say that 0 point in our displacement is at the platform, so up is positive, so that's a positive velocity vector that's initial, and our time is 6 seconds, and our acceleration is minus 10 meters per second squared, because that's always pointing downward. So what are we looking for? We've done step 2. Step 3 is, what are we looking for? We're looking for the final velocity, so we circled that. And then step 4 is we draw a line through the variable that's left, and that is the equation that we're going to use. Okay, so what equation is that? That's final velocity is equal to initial velocity plus AT. Okay, so let's just look at this, and that's just so for people who haven't memorized it. There it is. We're looking, oh, I'm sorry, we're drawing an arrow there. We're looking for final velocity. We're drawing an arrow through there, and this is the equation we're looking for to use. So we put in our information, the 3 bits of information that we have, and we stick it in there with our units, and it's already set up for V. So we've got 20 meters per second minus 60 meters per second. This second on the bottom cancels out, so we've got velocity and velocity, and so we end up with a final velocity of minus 40 meters per second. So what we're saying is that right before this, so there's our answer. So right before that rocket hits the ground, it's going to be minus 40 meters per second. So it goes straight up, comes straight down, and then continues on downward and picking up speed. Okay. Now, some of you all probably know that a quick way, there's a few interesting things here, and I don't like to use shortcuts, but I will throw a few in here for right now, just to sort of whet our appetite if you haven't seen these before. But anytime, whether you have a cannonball at an angle that goes up and comes down, or you have something that goes straight up and then straight down, the time that it takes to reach peak height, where the velocity is equal to 0, and the time that it takes to go from that point where it reaches peak height to come back to where it originated from, those times are exactly the same. Okay, so that's one thing that's worth noting. So that's the same here. At this point, this would be the peak height, like on a cannonball. So this time period here would be equal to this time period. Those two time periods are equal to each other. What goes up is the same time period as the time it takes to come down. The other thing that you could do real quick here is you can quickly find out how long it takes for this rocket to reach its peak height up here, where it would be a velocity at that point would be 0. The way you do that is that the initial velocity is 20 meters per second, and so our acceleration is minus 10 meters per second squared. So what does that actually mean? It means that every second the acceleration is taken away 10 meters per second of this velocity, of this initial velocity. So after 1 second, the velocity at that point would be 10 meters per second, and then after 2 seconds it would be 0, because every second it takes away 10 meters per second of velocity from our rocket, its initial velocity. So that means it takes 2 seconds to go up and 2 seconds to go down. So that means that at this point, when the rocket has come straight down again, it's got a minus 20 meters per second. Okay, the velocity going up is the same as that's initially going up, will be the equal to the velocity final that comes back, but it's going to be in the opposite sign. Okay, so we could actually, if we knew all these little things, we could even write another SUVAT problem. So we could say that if we know that it takes 2 seconds to go up and 2 seconds to go down, and that the travel time for this problem is 6 seconds, that means that at this point, when the rocket's right here and continuing downward to hit the ground, at that point it's going to be 2 more seconds. So we've got that. And then we have the initial velocity. If we pretend like when the rocket passes where the platform was, that we start our problem, then we can say our initial velocity is minus 20 meters per second. That's after the rocket's return. So we've got, and then we've got 2 seconds, we've got initial velocity of minus 20, and then we've got g. So we could solve this problem another way. We could still get the same answer. So I'm just wanting to show you that we could create another SUVAT problem. We have a problem like this, SUVAT. So at this point, when the rocket has just returned back, it's got, at that point we'll start our problem. And so our initial velocity at that point will be minus 20 meters per second. Our time is going to be 2 seconds because it went up 2 and came down 2, and we have 2 more seconds between there and there. So that's going to be the 2 seconds. Then we got minus 10 meters per second squared. And what are we looking for? We're looking for the same thing we're looking for here, final velocity. So we'll circle that, draw a line through that, and then we'll use this equation where v is equal to u plus at. So let's plug the information in. We've got, for here, we've got minus 20 meters per second plus minus 10 meters per second squared times 2. So that's equal to v, and so it's minus 20 meters per second plus another negative, that's 2 times minus 10 meters per second, 2 seconds. So that's another minus 20 meters per second, and that adds up to the same answer. So anyway, I kind of got off on a tangent there, but I did want to show you that yes, there are ways that you can find information with shortcuts, but I want you to stick to the original SUVAT method for right now. Okay. All right, next problem. I hope that wasn't too confusing there on that second example. Okay, here's another question from Khan Academy. Again, I mentioned that Khan Academy makes physics questions for the MCAT, the new MCAT. They make all kinds of great test prep for the MCAT. I've gone through it thoroughly, and it's really a wonderful site. Encourage you to go there. And it's reviewed by the AAMC, the people that make the MCAT test, to make sure the content is pertinent to the test questions they'll form on their exam. Okay, so we're looking at a physics question, a kinematic question from Khan Academy website. A Ferrari Enzo is able to reach a speed of 134 miles per hour, which is 60 minutes per second, from 0 miles per hour in 11 seconds. Assuming constant velocity, how far would the Enzo travel in this amount of time? Okay, so the first thing that should jump out at us is that this is a constant acceleration of an object. Okay, and we've got all this information that's SUVAT kind of information, velocities and time, and we're interested in how far. We're interested in displacement. It's a straight line, so we've got an initial position and finals, so that's a displacement. So we've got a SUVAT problem. Okay, so what do we know? One thing we do is, step 1 is we write SUVAT. Step 2 is put what we know down. We know that this went from 0 to this 60 meters per second in 11 seconds. So initial velocity is 0 meters per second. We have final velocity is 60 meters per second. Initial velocity, if I said it wrong, it was 0 meters per second. And then the time is 11 seconds. And that's step 2. Step 3, circle what we're looking for. We're looking for displacement. And step 4 is draw a line through the variable that's left and use the affiliated equation. And for this one, it's S is equal to final velocity plus initial velocity divided by 2, and that is equal, that right there is an average velocity, and that's times time. So we'll use this equation, and we will plug and chug. And so here's what we have here. We're using that equation right there. We're looking for that, and we'll go down here and As you can see, we just fill everything in. We don't have to even move anything around algebraically. So S is equal to final plus initial U and times time. And we put our units in, and we got 30 meters per second times 11 seconds. So seconds cancel, and we're left with 30 times 11, or 330 meters. So that's how a car that goes from 0 to 60, and it takes 11 seconds to do that, will have traveled a displacement, and it would be distance. They're both going to be equal in this case, because it's the actual path is equal to the initial and starting positions. So we made 330 meters in that time, and there's your answer. Okay, the last problem is a good problem. We haven't done any SUVAT problems where we use the second kinematic equation, so I wanted to take an opportunity to do that. So here we got a car with an unknown initial velocity, travels with a constant acceleration, that's important, of 2 meters per second squared. After 3 seconds, its velocity is 40 meters per second. So what is the car's displacement during this 3-second period? Okay, so we got a SUVAT problem because we got constant acceleration and all the information that we need to at least solve. We got 3 bits of SUVAT. One of the SUVATs, we got 3 out of the 5. So let's put what we know in. Step 1, we write SUVAT. Step 2, we put in our information. So we've got a constant acceleration of 2 meters per second squared. We've got a 3-second interval. We know the final velocity is 40 meters per second. And so this thing is going to the right, and it's going to travel for 3 seconds. And at the end, at that point, in the 3rd second here, okay, it's going to have a velocity of 40 meters per second. We don't know what its initial velocity was. We don't know that. And what we're interested in is what its displacement will be. So step 3, we're going to circle that, and then we're going to draw a line through the variable that's left, and that leaves us with the equation, the kinematic equation that's not really used that much. So what is it? It's S is equal to, displacement is equal to final velocity times time minus 1/2 AT squared. Okay, so we're going to go ahead and scroll down here. Here's this equation, and notice that this equation is very, very similar to that equation, almost identical. The only difference is these two have changed, and this is negative and that's positive. Otherwise, those two equations are exactly the same. We use the 3rd kinematic equation much more than this one, the second. In most problems, you'll see the 3rd being used more. Okay, so what we're going to do is plug in our information, and again, we don't have to move anything around. We put everything in and keep our units there, make sure they all cancel. 3 seconds times 40 meters per second, the seconds cancel. We have 120 meters minus, and we've got 9 seconds squared times 1 meter per second squared. So the seconds squareds cancel out, and we're left with 9 meters. So we get 120 minus 9 meters, so we get 111 meters is our displacement. Okay, so that would be our answer up here. That's how far it goes. Now let's take this problem and keep the same information, but let's find the initial velocity. Okay, so we're going to do the same problem, same setup, but now let's do the SUVAT for the initial velocity. So we are going to, step 1, put SUVAT in. Step 2, fill our information in. It's the same information. 3 seconds, 2 meters per second squared. We have our, our final velocity of 40 meters per second. We're looking, so that's step 2. Step 3 is circle what we're looking for. We're looking for initial velocity. Draw a line through the remaining variable that's left and use that equation. So that's v is equal to u, final velocity is equal to initial velocity plus at. So let's go down here and look at that there, and we're going to solve for this. So I just leave everything alone, fill the problem alone. I just fill it in and then shift things around. And when we do that, we're going to find 40 meters per second, and that's going to be minus, well, we got meters per second squared, again seconds. This will cancel one of the seconds on the bottom. So we end up subtracting 6 meters per second from 40 meters per second, and we find that our initial velocity was 34 meters per second. Okay, now that makes sense if you think about it. This is one of those problems that after you do SUVAT a while, you won't need to do it. You could do that in your head, but I want you to know how to solve this with SUVAT. But what you could do is, if you remember that, what does 2 meters per second squared say? That means that every second the velocity is increasing by 2 meters per second. So if we have a final velocity of 40 meters per second, and it took us 3 seconds to get there, because our problem started 3 seconds ago. So 3 seconds ago was the initial velocity. So we just count backwards by 2. So at the end of 3 seconds, it's 40 meters per second. And then if we count back 1 second, it's 38 meters per second. That's into the second. And then we go back, that's at the end of the second. Then we go back another second. At the end of the first second, it's 36 meters per second. So we're subtracting, what we're doing is we're subtracting 2 meters per second there, 2 meters per second there, and then we've got one more where we go back to the first 0 point in time, and that would be 34 meters per second. And there's one more minus 2 meters per second. So what do we do? There were 3 seconds, and for 3 seconds, each time we increase by 2 meters per second from 34. So we go from 34, 36, 38 to 40. 1 second, 2 second, 3 second. Adding 2 meters per second each time. So there is some common sense stuff to this, and it's only because this is the 4th video in this series that I'm starting to disclose some of this stuff. But stay with the SUVAT. Let's just do one more thing. Let's prove that the displacement that we calculated was right. So let's go down here. Now we've got more information than we need, but this is a good opportunity because sometimes you're going to have a kinematic problem where you'll have more than 3 bits of information, and then the problem is to figure out what equation to use when you got more information than 3 out of 5. So what we would do, and what we're looking for, is we're going to solve for displacement. Now we already know from the first part of this problem that it was 111 meters, but let's go ahead and pretend like we don't know that, and we calculated this from the second part of the problem. We were given these 3 initially. So let's figure out displacement. Well, what equation do you use? You could use any of these 4 because they all contain this information. We can't use this one because it doesn't have. Oh, wait a minute. We can't. I'm sorry. We can't use this one because it has no S in it. But we could use any of these 4. So we can't use. That's the only one we can't use because it's missing the S variable. So which one do we use? Well, we could use obviously want to use the one that's easiest to do the math in, and that would be this one. Okay, so let's just use that one. So we'll scroll down here and we'll plug that in. So we've got final velocity plus initial velocity divided by 2 times the time that was given, and so that's 74 divided by 2, so that's 37 times 3, and there it is. So we did calculate the right displacement from our first problem. Okay, so we covered a lot in this video. I'm trying to make these a little bit harder each time. Each time we have a new set of questions. So we'll hopefully you're getting convinced that the SUVAT method is a nice Nice security systematic method to have in your back as a tool in your back pocket when you take a time test in physics or on the MCAT. Okay, talk to you next time. Thank you. Bye-bye.